In this video, we'll continue talking about the second order ODE. The example we're going to use is the free oscillation. Assume we have a spring and this is in the unstretched mode. Now let's tie a weight to its end. Due to gravity, the spring will stretch. And this is the system in the static equilibrium mode. The extension due to the weight on the spring, let's call the distance S. Doing one more thing to the system, let's further apply a load to the weight and the spring will extend further. Let's call the extra extension Y. Now let go the system. The weight will continue oscillating, assuming there's no friction. Having a closer look at the system, we know there are only two forces acting on the system. One is gravity, another is the force from the spring. From Newton's second law, we know ma is equal to F. A, the acceleration, is y double prime. From Hooke's law, we know that ky is equal to F, where k is the spring constant, y is the distance. Since there are no other forces acting on the system, we call this system undamped system. Since the system is at equilibrium, the summation of the forces is equal to 0. Thus, my double prime plus ky is equal to 0. This form should look familiar to you. It is a classical example of the second order ODE. Let's look at an example. On the spring, and we tie that to a weight of 98 newtons. The weight will stretch the spring by 1.09 meters. The first question we have is, what is the natural frequency of the system? The second question is, if we pull the weight down with an additional 16 centimeters, what would be the equation to describe its motion, assuming the initial velocity is 0? If we use Hooke's law, we can easily calculate the spring constant, which is 90 Newton per meter. From first year undergrad physics, we learned the natural frequency can be written down as omega naught over 2 pi, where omega is equal to square root k over m. K is the spring constant and m is the weight. Doing some quick calculations, you will find out the natural frequency is 0.48 Hz, which corresponds to 29 cycles per minute. It is interesting to point out that the natural frequency is only a function of m and k. It does not matter how far you pull the weight, it will not change the frequency. However, if you pull the weight into different initial positions, you will get different amplitudes. Before solving question 2, let's revisit what we've learned in the previous video. In the general form y double prime plus y is equal to 0, we learned the solution can be written as y equals to c1 sine x plus c2 cosine x. In the spring oscillation system, it can be written as yt, which is as a function of time, equals to a cosine omega naught t plus b sine omega naught t. Then, writing down the oscillation equation is a matter of solving the initial value problems. We know at time t, we pulled the spring further down by 0.16 meters, then y naught is equal to 0.16. That gives us a equals to 0.16. We also know the initial velocity is equal to 0, then y prime 0 is equal to 0. That gives us b equals to 0. This gives us the final form of the oscillation equation, y equals to 0.16 cos 3t. The example we presented here is that we assume there's no friction. In the next video, we'll introduce a new term and to include friction to the oscillation.